Two-dimensional forces. The ability to resolve a force at an angle to the x or y axis to its components along the x and y axis enables the solution of more complex motion problems. First, a review of determining an object's acceleration in one dimension due to external forces, which are aligned with either the x or y axis, will be covered. For example, draw the free body diagram of a box being pulled along a rough surface. And what does that mean? That means there is friction between the surface and the box. After this is done, the acceleration along the x-axis will be calculated. Here's our free body diagram. Normal in the up direction, mg here. Here's your force applied, and friction force is in the opposite direction. We draw the friction force a little smaller because we're hoping and assuming that the object will be moving to the right. Now, find the acceleration of the box. Given that the applied force is 20 newtons, the box has a mass of 3 kilograms, and the coefficient of kinetic friction is 0.20. Solve the y-axis equation first for the normal force so that the friction force can be calculated for the x-axis equation. So we start over here. Sum of the forces in the y direction is ma, the acceleration in the y direction. Since it's not moving up and down, we set the acceleration equal to 0, so we get the normal force is mg. We substitute in our numbers, and here we'll be using g is equal to 10 meters per second squared, makes the math a little easier. And we have a normal force of 30 newtons. Now over to the x-axis. Once again, we start with Newton's second law. We have two forces. The applied force is to the right, friction force is to the left, so it's negative. That equals ma in the x direction. Substitute in the friction force, and then rearrange it so we solve for acceleration. It's always good to do that first, and then only put the numbers in at the very end. We substitute in our givens, do some calculations, and we get the acceleration in the x direction is 4.7 meters per second squared. Now we'll start solving problems where the applied force acts at an angle to the friction force. Okay, this would be our friction force, and here's our applied force. They are not parallel or perpendicular to one another. We'll take the case of a box being pulled along the floor at an angle. And here in bold print, always start problems with the free body diagram. The next critical step is to choose axes. Previously, the x and y axes were used since each axis lined up with the forces and the accelerations. You always have to ask, in which direction could the object accelerate? Then make one axis along that direction and the other one perpendicular. So, what's the answer for this case? How do we want to draw our coordinate system? This time, the x and y axes still work, since it is assumed that the box will slide along the surface, and it is not bouncing up and down, so the acceleration in the y direction will be 0 meters per second squared. Next, resolve any forces that don't line up with our axes into components that do. In this case, F applied must be resolved into F sub x and F sub y components. The normal force, mg, and the friction force are good as they are. They are already on the x or y axes. Once that is done, and that's done over here, we've replaced F applied with F sub x and F sub y, because when you add them vectorially, you get F applied. We will work with the x and y axis components separately. The problem is ready to be solved algebraically now. And here's our problem. Find the acceleration of a box of mass 3 kilograms when the applied force is 20 newtons at 37 degrees above the x-axis, and the coefficient of kinetic friction is 0.20. A similar problem was solved a few slides back, but the applied force was along the x-axis. This time, it's up here in the first quadrant. Once again, we will solve the y-axis first. Sum of the forces in the y direction is 0, as it's not bouncing up and down. And look here, this time, we have two forces in the up direction. the normal force, and F sub y. Those are both plus, minus mg because it's in the down direction, equals 0. So here's our normal force. It's not mg any longer. It's mg minus F sub y. And what's F sub y? That's F sine theta. So we plug that in, and we get a normal force of 18 newtons, which is less than the weight of this object. Right? The weight would be 30 newtons. So let's move over to the x-axis now. Again, Newton's second law. F of x minus Fk, friction force is max, and we substitute in the friction force here, which is mu k times the normal, which we get over here. We move this around a little to solve for the acceleration, substitute in our givens, and then find an acceleration of 4.1 meters per second squared. Now it's time to compare the differences when you pull a wagon at an angle versus pulling it horizontally. Here are the givens and the free body diagrams for the two problems that were presented. Here's the first one, where the force is along the x-axis, and here's the second one, where we have the force pointing up and to the right, and we've already broken it down here into its two components, Fx and Fy. And here are our calculations down here in red for the normal force and the acceleration in the x direction. What causes the different values for the acceleration? Friction was reduced when the box was pulled at an angle because the normal force was reduced. The box's weight, mg, was supported by the y component of the applied force plus the normal force. These are your two vectors up, and you sum them, and they equal mg. So with the algebra we did, we find that the normal force is mg, which is the weight of the object, minus F sine theta. So if the normal force is decreased, so is the frictional force. That explains the difference in the normal force, but since the friction force is greater for the object pulled along the x-axis here, this has a greater frictional force, why is its acceleration greater than the object pulled at an angle? That's not as easy to explain. It depends on the angle and the coefficient of kinetic friction. They work in tandem to determine the difference in acceleration between the two cases when the applied force is the same. Even though the friction force is greater for the object being pulled along the x-axis, it has a greater applied force in the x direction. Try solving the equations algebraically for the two cases and comparing them. And if you don't want to do that, just read this. The comparison shows that if cosine theta plus mu k sine theta is greater than 1, then pulling the object at an angle theta greater than 0, in other words, not pulling it horizontally, but pulling it up at an angle theta, that results in a greater acceleration. If this is equal to 1, it is the same acceleration, and if less than 1, then a greater acceleration results from the force being horizontal. Instead of pulling the object at an angle, what would happen to the acceleration of the object if it was pushed along the floor by a downward angled force? What would happen to the normal force and the friction force? We'll just use algebra this time, no numbers. Here's the free body diagram superimposed over the box. Next, the y components of the case will be examined. So normal is still the same, friction force is still the same, mg is still the same. Here's your difference right here. The force, the applied force, is down to the right. The angle between the applied force and the x-axis is theta. When drawing free body diagrams, the forces begin at the free body. So the force is slid down over here, resulting in the red-brown line to the right and down. The vertical angle theorem shows that this angle here is equal to this angle. They're both equal to theta. You've got this line going straight down. Here's your x-axis. So this angle here is the exact same angle as this, the vertical angle formula. In this case, the pushing force is also pushing the box into the surface, increasing the normal force as well as the friction force. So here's our forces on the y-axis. always start with Newton's second law. And the normal force is up. This time, Fy is down, as is mg, which is pretty much always down. That equals 0 because it's not moving in the y direction. And we have the normal force is now mg plus F sine theta. Now let's look at the x-axis. The forces on the x-axis are F of x minus the friction force equals max. So here's Fx, it's F cosine theta. The friction force is mu k times the normal, which we found on the previous slide. And then you do a little moving around of the variables, and you get the acceleration is F cosine theta minus mu k, parentheses, mg plus F sine theta, all divided by m. Let's summarize what we have here. The acceleration in the x direction for pushing an object is this. And the key thing here is F sine theta is a positive within the parentheses, which will be a negative once you multiply by this. So that'll subtract from your applied force in the x direction. And had we done the algebra for the pulling case, it's very similar. The only difference is right here, the F sine theta. And that has a negative sign. So given these equations, what can be said about the acceleration of an object when it is alternatively pushed and pulled with the same applied force? Here's our two equations. This is for pushing, and this is for pulling. First term is the same in both. Second term is different, right? This is when you push something, you have a larger normal force, so you have a larger friction force. In this case, you have a smaller friction force because of this minus, so you have a larger acceleration. So for the same force in each case, a larger acceleration results from pulling it. And that's why it's easier to pull a luggage cart in the airport than to push it. A smaller applied force is required to achieve the same acceleration. Example 1, friction force. A force of 35 newtons is applied to a box of mass 4 kilograms on a level surface where mu k equals 0.50. The box is accelerating in the x direction. Draw the free body diagram, find the normal force on the box, and then find the acceleration on the box. Answers will be on the next few slides. Free body diagram. Always start with mg. That's balanced off by the normal force here. Here's your applied force, and here's your friction force. The normal force is equal and opposite the gravitational force since the object is not accelerating in the y direction. It's not bouncing up and down. Since the box is accelerating the x direction, there must be a net force in the same direction. That means the applied force has to be greater than the friction force. The sum of the two forces has to be greater than 0. Find the normal force. Once again, start in the y direction. The sum of the forces is equal to ma. You have normal force minus mg equals 0. Normal force equals mg. Substitute in the numbers, and we get a normal force of 40 newtons. And of course, here's our givens. Find the acceleration of the box. We're going to use Newton's law in the x direction. Sum of the forces is ma. We have the applied force to the right, friction to the left. We substitute in mu times the normal for friction. Divide both sides by m. Then substitute in our numbers, and we get an acceleration of 3.8 meters per second squared.